Right, so if we consider this object and we want to figure out what the energy, kinetic energy of this object is, or any rotating object, that's going to be important consideration as we move forward. And so, we have that bike tire in class that we spin, and we can look at the energy of that. We could look at the energy of other kinds of wheels or irregular shaped objects like this one here. So every single point on the disk has a certain kinetic energy if you think about it, right? So if this object, irregularly shaped object, is looping around, looping around, each of these points here has a certain amount of mass. Every point there has a certain velocity to it. Therefore, each point has a certain amount of kinetic energy. So if we added up all the kinetic energies of all the different points, in this case, we're just listing 3 here, we could get a total amount. So in other words, the total amount of kinetic energy is the sum of all the individual masses times all the individual velocities squared. And I is the integer of all possible points, every single possible point. So we know V equals R omega, and so this is linear velocity, right? This is angular velocity. This is the radius. And so for every possible point with a velocity and radius, we can put in kinetic energy in terms of rotation. So we can do that. We'll put, instead of V, we'll have omega R. So like in here, omega R, omega squared R squared, right? Omega squared R squared for the second object, omega squared R squared, and so on for every single, possible point. Now, what we can do is we can factor out the 1/2 from every single one, because every single one has 1/2, and then every single one of those has the same omega. In other words, around here, it doesn't matter how far away you are from the axis of rotation, here, wherever, you're going to have the same angular speed as it goes around. So what we end up with then is 1/2 times the sum of all the possible masses over all the possible radiuses squared times omega squared. And when we talk about the moment of inertia, what we look at is just like we have all the masses added up over all the radiuses squared added up. On its own, we have the moment of inertia. So just this portion right here is called the moment of inertia. And the symbol is I. And the unit for that is a kilogram meters cubed. And so we're going to take a look at the significance of that here. Let's say we have one object. Well, we know that the moment of inertia then is just mr squared, because we know that kinetic energy equals 1/2 mv squared. So in place of v, right, we put in the omega, or r squared omega squared. So we have 1/2 m r squared omega squared, and so therefore the moment of inertia is just this middle portion. And then if there's just one object, you just have one mass here, and we've got that. So let's say that the mass here is 0.5 kilograms, and the radius is 2 meters, and the angular speed is 3 radians per second. We can calculate what the actual kinetic energy is, right, of the object. So we could do that. So kinetic energy equals 1/2 times the mr squared times omega squared. So 1/2 the mass, which is 0.5, times 2 squared times 3 squared. So we're left with 1/2 times, that comes out to be 2 times 9. And then we end up with, 9 joules? Okay. So that's the kinetic energy of this object as it goes around. All right, now we can consider if we have two different masses that are going around in rotation. So let's make the radius again 2 meters. The mass is 0.5 kilograms, and we'll say the angular speed is 3 radians per second. So now that we have these two masses, if we look at the moment of inertia, it's adding up both masses and then the radius squared. So we have both of these. So kinetic energy is 1/2 times the moment of inertia times omega squared. And so we have 1/2 times 2, so we got both of these, 2mr squared times omega squared. And we can work this out, 1/2 times 2 times 0.5 times the radius 2 squared times 3 squared. So 2 times 0.5 would be 1, and then 1 times 2 squared is 4, and then 4 times 1/2 would be 2, so 2 times 3 squared, which would be 9, so 18 joules. And so, and again, this is rotational, so these two objects are going around in rotation there. Okay, so now let's consider a ring. Let's say we have a ring that's in rotation with the center of rotation in the middle. And, the radius is the same. We're dealing with that. And so we're dealing with a lot more mass here, though. So R is the same for every single mass, right? So this point mass, point, all the way around every single point. And so what we do is we consider the entire mass, m, so the mass of the entire thing times r squared. And so that would be the moment of inertia for a ring. And so we can use that in terms of dealing with energy. For other objects, we need to consider the different shapes. It's not always easy to derive the moment of inertia for other objects. If you continue with your studies in math, you'll look at integration and that kind of thing where you can determine these things. But for a disk or a cylinder, we can get the moment of inertia by 1/2 mr squared, so dealing with the radius of the entire object, and then 1/2 the mass of the whole thing times r squared. For spheres, we can get the moment of inertia 2/5 mr squared. And rod, like this one here, that's rotating about an axis, 1/12 ml squared. And so those are different moments of inertia. You don't have to memorize any of those. They should be given to you as a given, or you can work your way backwards to solve for the moment of inertia for the different objects. But these are just a couple of common ones. And so the moment of inertia, both depends on the mass of the body and how the mass is distributed around the rotation. So each of these have a different amount of mass, spread out about an axis of rotation. The closer the mass to the rotation, less moment of inertia that there is. And so, the skinnier the cylinder here or the disk, the smaller the disk, the more compact it is. Or, the smaller the sphere, the more densely, packed it is. The shorter the lever, all of that plays into, the smaller amount of moment of inertia that's possible. So again, if we consider the energy of the system and we factor out the 1/2 and the omega squared, the middle portion is the moment of inertia. So whatever object it is, we can add up the total amount of energy by knowing the moment of inertia and, adding up the different moments of inertia to get the total amount in joules.